Welcome back, everyone. Our next speaker is Professor Allan MacDonald from the University of Texas at Austin. Professor MacDonald is well known for his contributions to many areas of physics, including the quantum Hall effect and twisted bilayer graphene. Today, he'll be telling us about quantum anomalous Hall effect, topological magneto-electric effect, and orbital magnetism. As usual, please put any questions you have during the talk in the Q&A box at the bottom of your window, and upvote questions there that you like. And at the end, I'll ask some of the top questions to our speaker. So thank you very much for being here, Professor. Please feel free to start when you're ready.
Okay, hello everyone. It would be more fun to do this in person, but we're getting used to this. I'm going to try to give a school type of talk. My topic is quite closely connected to the lecture you heard this morning from Andrea Young. I'm going to make some, some general remarks about orbital magnetism and about two other related things, the quantum anomalous Hall effect and the topological magneto-electric effect. And so feel free to interrupt me as I go. I'm going to start by quickly deriving the TKNN formula for the Hall conductivity. So this formula for the Hall conductivity is at the center of my lecture, and I'm going to write down a more general version of it a little bit later. And it's part of my motivation for actually going through this, so you'll believe me when I say it later. And this is a formula for the Hall conductivity of a two-dimensional insulator. And you can derive it, for example, from, it's really, it's linear response equation. And linear response for non-interacting electrons, we can write in terms of this handy summary of time-dependent perturbation theory, that the change in the linear response, change in the expectation value of some observable with matrix elements is equal to, is proportional, to the trace of the product of that observable and the change in the expectation value of the density matrix. And the summary of first order time-dependent perturbation theory is that the change of the density matrix you can write in terms of some difference of Fermi factors. So the response comes from transitions between non-interacting and interacting electrons. It depends on the frequency of the driving term compared to the energy difference between the states. And it depends on the matrix elements of the perturbation, whatever it is. So if we just plug into that formula for the case of interest, which is in the case of the Hall effect, it's the response of the X component of the current to the Y component of the electric field expressed as a time-dependent vector potential. I should say that the units are CGS when the prefactors are correct, and no signs are guaranteed. And I should say, okay, let me write down something else first. We know, as you know, normally express the conductivity in terms of a current response function current, X component of current response to Y component of vector potential, which couples to the current operator. And that gives us, for this current response function, you get E squared over A. So it's a current response function, CGS units, sum over states, just like up above. Difference of Fermi factors over energy denominator, and matrix elements of the observable is the velocity operator, and the vector potential, the observable we're interested in is velocity in the x direction. Y component of electric field couples to velocity operator in the y direction. And then if we remember that the electric field is the time derivative of the vector potential, then we have to remember two things to give the expression for the Hall conductivity. First of all, we have to remember that, whoops, okay, sorry about that. So we have to remember that we want to express the response not in terms of response to a vector potential, but response to electric field. That's just the definition of the conductivity. So converting from vector potential to magnetic field gives us those factors. And then we have to remember that, that there's so-called diamagnetic currents, that the current operator changes when the vector potential changes. And we can account for that simply by putting in the factor that makes the conductivity go away in the limit that the vector potential is not time dependent. So it doesn't give an electric field. And therefore, if we put those things together, this difference between finite frequency and zero frequency obviously vanishes when h bar omega goes to 0. And so by taking that difference in the denominators, you get a factor of h bar omega, and just putting these two energy denominators over a common denominator and taking the limit that the frequency goes to 0, you end up with an expression with the energy denominator squared. So what you get when you do that is an expression which is now becomes difference between occupation numbers, energy denominator in the 0 frequency limit squared, and again, this combination of velocity matrix elements. Okay, so that's an expression for the Hall conductivity that applies always. And if we now specialize to the case of a two-dimensional insulator, so state alpha, now we go to a two-dimensional crystal, I should have said. So the states are labeled by band indices and wave vectors in a two-dimensional Broussard. And we're going to simplify the matrix elements of the velocity operator between different states. by using this identity. So we take the derivative with respect to some component of wave vector. Let me just say the x component of wave vector to be definite. And obviously, this matrix element of the Hamiltonian between different bands is identically zero at every wave vector. So its derivative with respect to wave vector is also zero. But we can express it in terms of the derivative with respect to the wave functions. So for example, if we apply the product rule to this derivative we're taking here, if we differentiate with respect to the wave function on the left, then we can let the Hamiltonian act to the right, and we get a factor of energy. There's another similar term that where the derivative acts on the ket wave function in this expression, and turns out that you can express that just in terms of the other energy, because the Hamiltonian can act in the other direction, and then we have a term where the derivative with respect to wave vector derivative of the Hamiltonian with respect to momentum is the velocity operator. So, so the velocity operators between different bands that appeared in that expression by this identity are proportional to the difference in energy between these states times derivatives with respect to wave vector that act on wave function. And so if you plug that expression in, for the two energy denominators that appeared in the original expression cancel, and what you get, pulling everything together, is E squared over H bar. Sum over all states turns into a sum over bands, and an integral over the Brouin zone. These these operators are diagonal in momentum, and you get terms with Fermi factors. The energy denominators have disappeared, and once the energy denominators have disappeared, then for every occupation number, the sum over all of the states that are coupled to this one, you can just do that sum by a closure identity. There's nothing else left that depends on that factor, and what you get in the expression in the end, this Kubo formula, turns into derivative of the wave function, a property of just one band. Originally we had a difference of Fermi factors, and we can change the dummy index, and in each of those terms, Fn minus Fn prime, you can eliminate the, you can perform the sum over the bands that don't have the Fermi factor. And here I've just let the labels again be the same Fermi factor. And you get this simple expression in terms of integral over two-dimensional momentum of two derivatives with respect to momentum. So it's something that's almost zero, and you can, you can write this as, you can rewrite this as an integral of a curl of the Berry connection, which involves just one of these derivatives. So that integral of the curl you can do as a line integral of the Berry curvature. And in the end, what you get is E squared absorbing one of these 2 pi's into H bar to make it E squared over H. And what you're left with in the end is just the Berry phase that's associated with the rest of the, with integrating the wave function around the Brouin zone, which must be 2 pi times an integer, and that 2 pi absorbs the other 2 pi. So, so if you have a 2-dimensional crystal, as Thalles and collaborators taught us back in 1982, the Hall conductance is quantized. And of course, one example of that, Hall conductance quantization, which is just, follows from this simple linear response calculation, is that, if you have some type binding model for a band and you had to represent a magnetic field by Peierls phase factors, then you get 2D crystals with quantized Hall conductance in a magnetic field, which is what they were most interested in at the time. But what we're most interested in today, and which the possibility of was emphasized first by Duncan Haldane a few years after Thalles and collaborators, is a quantized Hall conductance in the absence of a magnetic field. So, of course, as you're no doubt aware, the Hall conductance which is the antisymmetric part, strictly speaking, of the conductivity tensor, can only be non-zero if time reversal symmetry is broken, but the band Hamiltonians of any magnetic system have quite generically broken time reversal symmetry. And so in principle, any magnetic system in 2D can have a quantum anomalous Hall effect. And okay. And you heard this morning about, let's say the second, I believe, experimental realization of the quantum anomalous Hall effect, which is the quantum anomalous Hall effect in twisted bilayer graphene. So now I'm going to talk about edge currents. So let's say I have a 2-dimensional electron system. It has a boundary somewhere, and so I want to calculate I'm going to calculate edge current response now to electric potential. So locally at some point in the edge, I can say the local boundary I can choose to be along the y-axis. So this is outside the sample. And this is inside the sample. I want to ask if the Hall conductance changes in response to a uniform space-independent change in the electric potential in the interior of the sample. And so I can do that by making a plot. Let's say this is X in this direction, and this is the sample edge. And I'm going to plot some potential and choose it to be 0 outside the sample. And so I'm going to turn it on inside the sample by somewhere, far enough from the edge, smoothly turn on some potential V. So the total edge current that flows in response to turning on this potential is the integral of the current density of X of the Hall conductance. Let me just call it sigma Hall, which is, implicitly here, I'm interested in insulator. If there's a small potential change in an insulator deep in the bulk of the system within the gap, it's not going to induce any current in response. The current will come only here where I've let the potential gradually go to zero. So there's an electric field here, and put a 1 over E in the denominator just to make a distinction between the potential energy of the electrons, which is V, and the electric potential. But the current density then at a given point is proportional to dV dx. That's the electric field perpendicular to the boundary, and it will drive an edge current along the boundary at any point, given by this integral. So that's sigma Hall over E times V, okay? So that's, I said the Hall conductance is E squared over H. So this means E over H times an integer times the potential. So I'm going to use an expression like this in a little while to talk about the topological magnetoelectric effect and its relationship to the quantum anomalous Hall effect. Try to talk about the two things in the same way. Okay. So that is current flowing at the edge in response to a potential. Now I want to make a very similar argument, and that is do a very similar calculation of current flowing not along the edge, but current flowing across the edge. In response not to a potential, but to not to a position-dependent electric potential, but to a time-dependent magnetic flux. A time-dependent magnetic flux will give an EMF, effective electric field, at the edge, along the edge, in this case, due to the time-dependent electric field, and it's, that electric field is 1 over C d phi dt, so the electromotive potential is proportional to the time derivative of the magnetic flux, and that's spread out across the entire edge of the perimeter of the system. And let me just, for convenience, assume that it's a circle. And so what happens in this case, in this type of argument, which is often used in similar arguments in quantum Hall effect. For example, it's one way to understand fractional charges. Then if I change the magnetic field that's going through the system, then there will be a effective electric field that's directed along the edge, and it will make charge flow perpendicular to the edge, and that the total, if I integrate again across around the entire edge, canceling this factor of the perimeter, then the total charge that's induced is proportional to the Hall conductivity, proportional to this EMF integrated over time. Integrated over time, instead of d phi dt, I just get phi. And if I put all the factors together, I get E over HC times A. This is for times the quantized Hall conductance N times B, times, let's say, if it's a change in field, then the change in field is given by this expression, which I can write as A over magnetic flux quantum times the Hall conductance integer. So that's the derivative of N with respect to B. So this is, if I have the two-dimensional insulator that's in a quantum anomalous Hall state, I'm going to assume N is 1 just to be lazy, then dNdB is proportional to area. So the density is derivative of density with respect to field is just 1 over magnetic flux quantum. If I just think about this thermodynamically, in a grand canonical ensemble, the NdB is N is minus derivative of the grand potential with respect to chemical potential. And so I can recognize this quantity A over phi naught using the Maxwell relation as dm d mu, okay? So when I have a quantized Hall conductivity, I have a orbital magnetization due to currents flowing in the system, currents flowing around the edge. And the derivative of the orbital magnetization with respect to the chemical potential is just 1 over the flux quantum. And this is actually, so if this orbital magnetization is coming from currents circulating around the edge of the sample, then this relationship also tells you that when you have a quantum Hall effect, then the derivative of the edge current with respect to chemical potential is given by this quantized expression. What this says actually is, if I, okay, let me just make a remark that this is really what people measure when they measure the quantum Hall effect, because, typical measurement, 4-point measurement, you have a current source, current drain, and then you measure the voltages, 2 different places at the edge, and by charge conservation, the current at this position at the edge and this position at the edge differ by an amount that you know simply by the external current. And if the edges are locally in equilibrium at some chemical potential, what you actually measure is the difference of those chemical potentials. That's the Hall voltage. So it's actually this d edge I edge d mu is exactly the thing that's measured experimentally. And And so what we've shown then from these two arguments is that if I have a quantum anomalous Hall system, or if I have any two-dimensional insulator, then the edge current depends on the chemical potential, and it also depends on what I'll call the electric potential, electron potential, maybe, by which I mean simply the potential energy function seen by the electrons. So it depends on both, and if you put in the signs correctly, of course, it can only depend on the difference of these two quantities. And if you change the electric potential in the universe or in the interior of the system, at least by some constant, and shift the chemical potential by the same constant, nothing depends on the zero of energy. So as usual in transport, we know that these things, currents depend only on these well, maybe I shouldn't say that, but this current depends only on the difference. And so the quantum Hall effect is a measurement of how the current depends on the chemical potential. I'm going to say that the topological magnetoelectric effect is a measurement of how the current depends on the electron potential. And so I will come to that presently, but I want to make a small digression on the quantum anomalous Hall effect in magic angle twisted bilayer graphene. So first of all, let's just talk about bilayer graphene, which Andrea mentioned in his talk this morning. Simplified version of the band Hamiltonian for bilayer graphene is that it's a two-layer Hamiltonian. There's a layer degree of freedom. The coupling between layers is second order in momentum. And so this, in this, what people sometimes call quadratic Dirac Hamiltonian, the mass term, which is the difference in energy, proportional to the difference in energy between the two layers, is something, of course, that's very easy to tune experimentally. I want to say that I'm going to give an argument that the valley projected Hamiltonian. I should have said that this single particle Hamiltonian is, sort of an envelope function description, and it's applies for quantum states with these momenta are measured from one corner or the other of the graphene Brouin zone where the low energy states exist. And so this is a valley projected Hamiltonian. The Hamiltonian projection to the other valley differs by time reversal symmetry. And what I want to emphasize here is that these valley projected Hamiltonians always have non-zero Chern numbers. Chern number is the Berry phase for integrating around the perimeter of the Brouin zone, and we wrote down the expression for it in terms of the derivatives of the band states with respect to wave vector. That particular derivative, as you all know, and I didn't say, is the Berry curvature. And for a two-level system like this, two layers for each momentum, there's of course a very simple expression for the Berry curvature in terms of the dependence on momentum of the block sphere orientation for these two-level systems. And the result is that that the Berry curvature, the local contribution to this integral from each k, is just proportional to the area on the block sphere that you map out in each each little interval of momentum. Here's the block sphere for this two-level system. For m is equal to 0, this would be top layer here, and this is bottom layer. And we make a block sphere normally where, let's say, one of the layers is the North Pole, one of the layers is the South Pole. And for m equals 0, all of the wave functions are half in one layer, half in the other. But if I have an energy difference between the two layers, then for very small k, it's very easy to polarize the wave functions, let's say, of the valence band of the lower energy state in this two-level system. The way I've written it would be at k equals 0, it will be at the South Pole, and for a given point in k, this expression is how much area on the sphere you map out for a small region of momentum. So this is dxn, let's say, and dyn at some point on the sphere. This is the area that you map out on the sphere. And just from this Hamiltonian, it's very easy to read off what happens when you integrate over a large region of k. At every k, when you go around a circle, you go around a line of longitude in the sphere because it's determined by the phase of this off-diagonal term, which is the only thing that's changing in this direction. So when you do the integral over all k, you see that you get a Hall conductance of 1 unit. And of course, there's something slightly fishy about that because in the case of bilayer graphene, in this continuum model, momentum goes out to infinity. So there's no Brouin zone. So when I say it's quantized, I'm just imagining that this model applies out to infinitely large momenta, which it doesn't. But nevertheless, it's true that when you make, one of the things you do when you have a Moire superlattice is you make a Brouin zone in this momentum space. And it turns out that normally for the states close to the Fermi level on either side in twisted bilayer graphene, for any model you might want to make of those states, that in most cases they have the same Hall conductance quantum number as bilayer graphene, and that were depending on the sign of the potential difference and the valley, the Hall conductance of the valence and conduction bands are, plus or minus 1. And right, so roughly, that's where the quantum anomalous Hall effect comes from in magic angle twisted bilayer graphene. Similar sort of argument, says that the Hall conductance is half quantized, and I'll come back to this when I talk about the topological magneto-electric effect. If I have two single layer, if I have a single layer graphene system, a single Dirac cone, that gives a half quantized Hall effect, yeah, and so you need two of those, of course, to make a legitimate crystal. And I was going to say one thing here. Yeah. Okay. Yeah, I remember. So, so in bilayer graphene, the bands tend to have non-zero Chern numbers, and so it's very natural that if these systems have a ground state that is valley polarized, a valley ferromagnet in the language that Andrea was using, then they will have a quantum anomalous Hall effect. That if both valleys are occupied, then the two valleys have opposite sign of Chern number because they're related by time reversal, and the way you get a non-zero result is simply by forming this ferromagnet-like state, which occupies one and not the other. And okay, so I want to make one more remark related to the quantum anomalous Hall effect in magic angle twisted bilayer graphene. What the Moiré superlattice is giving you is both very flat bands, so it's easy to satisfy the Stoner criterion and get a valley ferromagnet. And it's also giving you a Brouin zone, so you're really on more solid ground to say that quantum Hall effect is quantized. And as I've been saying, that that when you have a quantum anomalous Hall effect, you have a property that's of this orbital magnetism that's very different from what's familiar to us in spin magnets. That means, in particular, the magnetization depends on position within the gap. And there's a jump in magnetization across the gap, which is proportional to some universal numbers and the energy gap. And I think that magic angle twisted bilayer graphene, someone can correct me if they want, but I think it's the first example in nature of really orbital ferromagnetism. And it has this strange property that the magnetization jumps across the gap. And this becomes, really interesting phenomenologically, as Andrea was explaining, if this jump is sufficient to change the sign of the magnetization. And the next remark I want to make is just to say that this is actually a tricky quantitative question, whether or not this jump in magnetization is sufficient to change the sign. And the fact that Andrea actually observed a change of sign of magnetization, a prong, going from a weakly N-doped insulator to a weakly P-doped insulator, actually says something microscopic about the ferromagnetic state. So let me make this remark now. And for this, I'm going to write down an expression. The expression for orbital magnetization is that Andrea talked about this morning. I'm not going to derive this, but it's related to the derivation of the Hall conductivity, a little bit more complicated, derived by actually, orbital magnetization is interesting, wasn't really so well understood from the dawn of solid state physics until at least this century, thanks to the work of David Vanderbilt, Resta, and my colleague Chanu and others. This is the band theory expression for orbital magnetization. Just depends on the band structure, energy as a function of momentum. Also depends on these velocity matrix elements between between occupied and empty states. And I want to make the following remark. The orbital magnetization is 0 if the chemical potential lies exactly in the middle of the gap, and you have particle-hole symmetry. So if these two properties are satisfied and M is 0 in the middle of the gap, then definitely when you go from weak N doping to weak P doping, definitely that the sign of the magnetization changes. And so let me say mu is mid-gap, and I'll choose that as my 0 of energy. Then I can drop mu from this expression. And if I have particle-hole symmetry, that means for every band state, there's every conduction band state, there's a corresponding valence band state with the opposite energy, choosing again the 0 of energy at mid-gap. And in this expression, the contributions you can show, come from transitions between occupied and empty states. And if chemical potential is at the middle of a gap of a particle-hole symmetric system, then I'll call the negative energy states the valence bands and the positive energy states the conduction band. And for every pair of them, I can switch the band indices N and N prime between conduction and valence. Obviously, the energy difference squared doesn't change. The sum of the energy changes sign, and you can show that these matrix element factors also say the same. And so that's how this property emerges. And So that's the condition, so if the closer you are to particle-hole symmetry, the more certain you are that the magnetization will jump across the gap. And I think you are aware that, many of you, that the single particle models that are the starting point for the theory of magic angle twisted bilayer graphene are not particle hole symmetric, but they're nearly particle hole symmetric. And if you make them a little bit more realistic, they're not so particle hole symmetric, but they're maybe close enough that that if you look at the contribution to the magnetization from a given valley, and let me forget about spin now. So imagine I have two bands labeled by valley, and I'll talk about the case where most of the observations of the quantum anomalous Hall effect been done. I'm going to write here on the left, I'm going to write some sketch of the density of states for valley K, and over here for valley K prime. And as I said, the quantum anomalous Hall state is one type of valley ferromagnetism where if it's an insulator, you have only filled bands or empty bands, but more bands are occupied for one valley than the other. So let me imagine that, I'll do it this way. So here is valley K. It's got two bands close to the Fermi level, two flat bands. So here I'm, using some sort of quasi mean field picture where when I have different occupations of the bands, I have different energies of the bands. I've actually drawn the case where only one of these four bands is filled, but it's the same as when I had three. So let's imagine as in my sketch, I occupy only one of these four bands. I occupy the valence band for valley K, but not for valley K prime. And so if I have an insulating state with filling factor 1, the Fermi energy has to lie somewhere in this gap. The closest state, the conduction band, is actually in this sketch in the other valley. Okay, so this is valence, it's conduction. So in valley K prime, neither of these bands is occupied. This band pair typically has, Chern number, let's say it's +1 here, -1 here. Chern number -1, integrated Berry curvature. So the other valley always has the opposite Chern numbers. And so this would be, as I've drawn it, a quantum anomalous Hall state with Chern number -1. And there's no contribution to the magnetization from these states since they're not occupied. And no contribution to the Hall conductivity. And in the region that's actually in the gap, though, the exchange splitting, let me just call it U, the amount by which the energy of the occupied valley is lowered by exchange in some mean field description matters because at the value that I've sketched, for example, the region of energy that is actually in the gap of this valley polarized insulator does not include the chemical potential at mid-gap for the other valley. So in this case, when the, as you change density, when the chemical potential jumps from here to here, nowhere in this gap will you get a zero magnetization. So the magnetization would not change time. Michael, how much time do I have?
It's 1:56, so you have about 20 minutes.
Okay. Okay, so in my remaining time, I want to discuss the topological magneto-electric effect using the same kind of language. It's kind of interesting that the quantum Hall effect, I don't actually know the current number, maybe one of you does, but I think it has a bigger, is measured with amazingly, to an accuracy of a part in 10 to the 10, which is incredible. And, it's a gift, from God to all of us that, this quantity, which is really a topological index, is actually a conveniently measurable quantity that can be measured with incredible precision. Even when you have a quantum Hall effect due to magnetism, and the best example is the quantum anomalous Hall effect in magnetized topological insulators. I'm not sure I know how far people have gotten in making this accurate. I think a lot of this work was done by David Goldhopper Gordon and collaborators. But the quantum anomalous Hall effect in magnetized, surface magnetized topological insulators has an accuracy of about a part in 10 to the 6th, if I'm up to date. And but the topological magneto-electric effect has basically not been measured. And so part of this discussion is sort of related to thinking about, how to measure this system. Of course, a lot of the problem is materials, and maybe this discussion will help to say what materials properties are desirable. Okay, so here's the equation I'm going to use to think about the topological magneto-electric effect. I'm going to think about a thin film in which I'm interested in measuring the quantized topological magneto-electric effect as a quasi 2D system. So it's 2D with some finite thickness, maybe very thick, but still I can think of it as quasi 2D if I want. And it's an insulator, and so the magnetization is produced by currents that flow along the sidewalls. And there's a generalization of the argument I gave you before for a simple 2D system, slightly generalized formula. For layer resolved. Here I'm just making this z direction coordinate discrete, partly because if I want to do some numerical tests, I would use a tight binding model, but partly just to have 2D units for this conductivity. So I can make a non-local version of the expression I gave you before, in which I allow the electric potential in the bulk to vary from layer to layer in some arbitrary way, and I measure the current in each layer. So this is some sort of non-local sidewall current conductivity, and the expression for this is just a layer resolved version of the the bulk Hall conductivity that I derived painfully at the beginning of the lecture. Same derivation. You can just let the perturbation be layer dependent electric fields, and you can let the observable be layer dependent currents. And so one thing you know about this is that that sum over all total current and potential that's independent of layer. This is just the regular Hall conductivity. So this is just E squared over H times an integer. And we know actually from experiment that let me just say a couple more things. Okay, I'll say this now. So we know that if we have a topological insulator from, for example, the bismuth telluride family, optimized within that family, I guess it's usually bismuth, antimony, 50-50 roughly, and telluride that's best. And that in this case, when the magnetizations in a thin film on both the surfaces are parallel, that's how the quantum anomalous Hall effect is realized in topological insulator thin films that are either magnetized throughout or surface magnetized. Okay, so n equals 1 is quantum anomalous Hall effect. N equals 0. People have good evidence experimentally that you can create a magnetic configuration in which you have a regular quasi 2D insulator with no quantum anomalous Hall effect. And that's what people refer to as an axion insulator. Because it's a topological insulator with surface magnetism, and because if the magnetizations in bottom and top are opposite, you could imagine continue them across the sidewall without and always being outward or inward directed. So that will give an insulator also on the sidewalls. And so those states have been seen, which look like insulators. But the topological magnetoelectric effect has not been measured. And yeah, so I want to make one other remark. If I have a topological insulator and I don't have surface magnetism, then I don't have broken time reversal. And there are no sidewall currents. This non-local Hall conductivity is just identically equal to 0. Everything is driven by the surface magnetism. And okay. So I think I'm getting a little short on time. And so maybe I'll try to make just one more point if that's okay, Michael.
Yeah, you have about 10 minutes still.
Okay. Okay, so so I'm going to make an argument that this non-local sidewall conductivity which is, basically projected current electric field response function, that it has some local property, that it depends on the material around it. So for example, if I have thick films, then in the middle of a thick film, there's no broken time reversal. And this quantity will go to 0. In other words, time reversal symmetry is broken at the surface, and that with some non-localization length that depends on microscopic details and may even be large, this sidewall conductivity is non-zero only for L and L prime, close to top and close to bottom in some sense. So that means that so these kinds of local properties, I think, are, for example, implicit when you if you represent surface magnetization by introducing a Magnetoelectric term in the electromagnetic Lagrangian with a E dot B term, with E and B at the same position. I think then these local properties are implicit there too. So when this is true, then that means that sigma, the total Hall conductivity, by which I mean sum over all layers of sigma L, L prime, can be separated into a top contribution, let me just use one letter, and a bottom contribution. Where this is summed over some length related to the top. So let's just believe that for the moment. Then, each of these quantities, the total and the top layer and bottom layer, are related to the surface magnetism, and for example, and they also must satisfy a time reversal property, that if you change the sign of the surface magnetism, then the sign of the Hall conductivity will change. And so So what that means is, let's say, for example, I take the quantum anomalous Hall state when the magnetizations on the two surfaces are the same. And that means sigma, which is sigma top, which depends on, let me just call it, call this J. Depends on the magnetization at the top. No, I'll call it N, sigma top, N top, plus sigma bottom of N bottom. So that's the non-locality property. And, for a finite thickness film, this sigma, if, for example, I could choose to define this as summing over the top half of the film, then, at any finite thickness, this will depend continuously on the strength of the magnetization or exchange coupling to the band states, and will pass through zero when the magnetization is equal to zero. But the quantum Hall effect tells us that that I can change, that this is always E squared over H. Let me call it 1, or let me assume that the Hall conductance quantum number is 1. So these have to add up to E squared over H when they add together, and independent of any detail near the top surface or near the bottom surface. And the only way that can be true is if they contribute equally. Okay, so that is a different version, if you like, actually one that I find easier to understand for the argument that that there's a time reversal symmetry property that says that the that the Hall conductance quite generally has to be half quantized. It certainly you can show, give a strong microscopic argument that it's half quantized in the limit of weak magnetization. Yeah. So what does this mean? So let's say that, so let's imagine I have I'm going to go to a different page. A thin film with, so let's say magnetizations on the surface. Let's say they're located, directed oppositely. So let's say there is this non-local response comes from some, to within some accuracy, comes from some region near the surface. And the distance from the middle of this region near the top to the middle of this region near the bottom is, let's say, the thickness of the film minus twice the sort of non-locality length of this edge response. And if I plug that in my formula, then I would get, and I add as a perturbation, not a chemical potential, but an electric potential, then I'll write down the formula again. This is the sidewall currents. It's also up to some constants, the magnetization. Here we're interested in response to electric potential at, this is an equilibrium thing. The whole thin film can be in equilibrium at some chemical potential. And so this will end up being, you know, E over H times the difference between the electric potentials at the top surface and the bottom surface. And so what it really measures then at a finite thickness is not the width of the entire film, not the total, you know, electric potential across the entire film, but something smaller than that. And that gives a 1 over thickness correction to the magnetization that's induced in this system by an electric field, which is what you always see in numerical calculations. And in numerical calculations, it turns out that this width is typically, you know, a couple of nanometers, a couple of quintile layers or something. So if we wanted to get this, you know, sort of correction factor, non-universal factor, to be a part in 10 to the 6th, then we'd have to have films that have a thickness of millimeters instead of nanometers. And it's, you know, it's hard to make films of this thickness. So maybe I won't, you know, talk about the materials challenges. There are 2 types of materials challenges that as the films become thicker, then what's going on in the bulk matters more. And in most of these, you know, in the common topological insulators, there is, as many of you know, there are anti-side defects in the bulk, which give a non-zero conductivity typically, and so that makes a limit on, you know, how thick you can make the film. Maybe MBE growth of these films is also a limit. Not sure, you know, about bulk samples. Maybe with and the other, you know, difficulty in you know, measuring accurate topological magnetoelectric effects is that we need surface magnetism, and we probably need that surface magnetism to be at least moderately uniform, and that may be a challenge. But I do think that there probably are ways forward, and that it's useful to think about the quantum anomalous Hall effect and topological magnetoelectric effect as 2 sides of the same thing. So I'll stop there, Michael.
Great, thank you very much for a wonderful talk. I think we have a couple minutes we have about 10 minutes for some questions for the next talk. So first question we have here is about the m equals 0 derivation. Why is m equals 0 when the chemical potential is exactly in the mid-gap? There are circulating edge currents that can, are there circulating edge currents that can contribute to orbital magnetism? And there's another question which I think is related. Can you clarify what determines the precise value of the chemical potential within the gap? In an insulator at T equals 0, it's not quite clear how to pin the value of mu.
Yeah, so let me take those one at a time. Okay. So, you know, the property that m is equal to 0 when the chemical potential is at mid-gap comes from the microscopic expression for the magnetization. There might be, sort of a, it probably, there's probably an argument, a simpler argument you could make non-microscopic, that if you occupy all states in the entire Hilbert space, M is 0, and if the contribution from particle hole symmetry says the contribution from the conduction valence bands are the same, then they must both be 0. But anyway, that's a property of any model that has particle hole symmetry. So the chemical potential of an insulator is not defined in the limit T goes to 0. That was the other remark. And but if you have a system with mu is equal to 0, or sorry, a quasi 2D system with 0 Chern number, the magnetization doesn't depend on mu when mu is in the gap. I should have emphasized that probably.
Thank you. Let's see. Someone asked, is there an analog of the topological magneto-electric effect for topological superconductors?
Yeah, that's a great question. I'm going to think about that. Thank you for the question.
Nice.
It might depend. I guess, there are many things, people mean many different things by, there are many different types of topological superconductors. Maybe the answer depends on the sense in which the superconductor is topological. But anyway, that's a great question.
There's a question here that was actually asked before the talk, so it's not exactly, but it's been upvoted. There have been several works showing that electron-phonon interaction is significantly enhanced and is a relevant coupling close to the magic angle and twisted bilayer graphene at low temperatures. Which of the experimentally detected phenomena in TBG, other than superconductivity, could possibly be a consequence of electron-phonon coupling?
Well, certainly, electron-phonon coupling plays a role in the electrical resistivity. There's maybe it's not clear that electron-phonon scattering is the only thing that's limiting the electrical conductivity, and it no doubt plays a role in superconductivity. Whether it's the dominant role, I don't think that's 100% settled yet.
Someone asked, would you expect the topological magneto-electric effect can be realized in 3D systems? What is the role of dimension playing here?
Yeah, so topological magneto-electric effect is really a property of 3D topological insulators that have broken time reversal at their surfaces, and but in a certain sense, it's maybe this is always, it's got to do with it's manifested in phenomena that occur at the surfaces of those 3D systems. And for the case of thinking of a 3D system as a surface, as a quasi 2D system with a large but finite thickness, that's really the point of view that I was trying to take. So I was really talking about the 3D topological magneto-electric effect. Hi, Pablo.
I think maybe I'll ask one more in the interest of letting people have a little short break before the next one. Someone asked, does the quantized invariant of the TME admit an inherently many-body formulation, such as the Kubo-Chern formula for the quantum Hall effect? That is, without leveraging the mean field or effective band theory type arguments.
Yeah, so I can say I don't know what it is off the top of my head. Maybe somebody actually knows whether this is, there isn't a positive answer to this in literature. You certainly would would think that you don't have to use the single body language. Yeah. So I asked the questioner to share with me if they discover the answer to that question, or if anybody knows the answer, that they share it with both of us.
Great. All right, so I think maybe we should take a couple of minutes. So thank you very much for a wonderful talk.
Yeah,
and
my
for
pleasure.
answering
Thank you, everyone,
questions.
for listening.
Really appreciate
and
it.
feel free to follow up by email. Is there anything you want to discuss?
Yeah, there were two questions we didn't have time to get to, unfortunately, but maybe they can
Okay.
email if they want to. Okay, thank you very
Okay.
much. We'll have
thanks,
a
Michael.
4-minute break, and then we'll reconvene at 2:30 for our final talk.